everyone. Today I'm presenting Talos, neutralizing vulnerabilities with security workarounds for rapid response. So as we know, patching is the usual way to fix a vulnerability. When the vulnerability is discovered, the vendor would need to release a patch, and then the users would need to apply the patch to fix the vulnerability. However, there often exists a delay between the discovery of the vulnerability and the release of the patch, which we call a pre-patch window. And attackers can exploit the vulnerability during this window. To understand more of this pre-patch window, we studied 131 recent vulnerabilities and found that the delay is significant, which is 52 days on average. And 1/3 of them were patched 30 days after their discovery. A recent study published in IEEE in 2012 indicates similar results. To understand the cause of pre-patch window, we studied the bug report to understand the time spent on each step of releasing a patch, which consists of vulnerability triage, constructing the patch, and the regression testing to ensure the patch doesn't break any functionality. So we found the bug reports for 21 of the 131 vulnerabilities, and they show that 89% of time was spent in constructing the patch. For those took more than 1 day to patch. And 9 of them took between 2 to 6 attempts to patch correctly, which is illustrated from the comments from one bug report. So as we can see, the comments from the developer include this updates the previous patch, this patch builds on the previous one, and one of the very last comments from the tester is still, I'm afraid I found a bug. So we conjecture that the complexity of constructing a correct patch is the major cause of pre-patch window. To address the pre-patch window, users often resort to configuration workarounds, which leverage existing configuration settings to neutralize vulnerabilities. So as we show one example on the figure at the bottom, we have one Apache HTTP server, which has one vulnerable status module. So one malicious request is sent to the Apache HTTP server and get processed by the vulnerable status module. Sensitive data will be leaked. Fortunately, the users can change configuration settings to disable the vulnerable status module, so that the malicious request will not get processed by the vulnerable module and simply get rejected. However, configuration workarounds have poor coverage. We studied 182 vulnerabilities and found that only 25% of them have configuration workarounds. So the vast majority of vulnerabilities do not have configuration workarounds. To address the drawbacks of patching and configuration workarounds, we propose security workarounds for rapid response, or SWR. The objectives of SWR include security. We'd like to neutralize vulnerabilities rapidly without introducing new bugs or vulnerabilities. Coverage, we'd like to cover many more vulnerabilities than configuration workarounds. Low cost, we like to be able to apply SWRs to existing applications with minimum engineering effort. And SWR neutralizes a vulnerability by disabling the execution of vulnerable code. As we show on the figure at the right, we see one SWR, which is a simple return statement, is instrumented into the vulnerable full function, so that the vulnerable code will never be executed. It is important to note that the SWR has to return an error code that can be recognized by the function's caller, which I will explain later. So the mechanism of SWR is simple but effective. We propose two deployment modes of SWRs to vendors and developers. So the first mode is in-place SWRs. In this mode, SWRs are pre-installed into an application. As shown on the figure on top, each green box represents a part of the code that's protected by one SWR. And they are deactivated by default, so they do not affect the execution of the application. And when one vulnerability is discovered in the application, users can simply activate the corresponding SWR to neutralize the vulnerability on the fly. However, in-place SWRs can incur runtime overhead because they are pre-installed into an application. The second deployment mode is patch-based SWRs, which are only issued after vulnerabilities are discovered. So as we can see from the figure at the bottom, when a vulnerability is discovered in the application, the users need to install an SWR for that particular vulnerability to neutralize the vulnerability. However, the advantage of patch-based SWRs is that they incur no runtime overhead. To show how SWR can reduce the pre-patch window, we compare different approaches to addressing a vulnerability. So for full patch, the developers need to identify the location of the vulnerability, which can often be found from the bug reports submitted from end users. Then the developers need to figure out the cause of the vulnerability and construct a patch. Then the testers need to run regression testing to ensure the patch does not break any functionality. And finally, the users can download and install the patch to fix the vulnerability. For in-place SWR, similarly, the developers need to identify the location of the vulnerability. However, with the help of an automated tool, they can easily identify which SWR can be leveraged to neutralize the vulnerability. And with this information, the users can simply activate the SWR on the fly to neutralize the vulnerability. For patch-based SWR, again, developers need to identify the location of the vulnerability. And also with the help of automated tool, developers can easily generate an SWR for this particular vulnerability. And the users can then download and install the SWR to neutralize the vulnerability. As we can see, both modes of SWRs would actually eliminate these three time-consuming steps involved in releasing the full patch. Thus, they would reduce the pre-patch window. During our design of SWR, we faced two major challenges. The first challenge is how to disable code execution safely. We'd like an application to continually run after an SWR has been activated. And we also want SWR to be unobtrusive, which means they should not cause loss of major functionality. The second challenge is how to minimize human effort in generating SWRs. Our intuition is the existing error handling mechanism in applications can be leveraged to address the challenges. So as we can see on this figure, which are code from the Lite HTTP server, which shows the error handling code already present in the Lite HTTP web server. So the Advantages of existing error handling mechanism are that, first, they are readily available. Almost every decent application has error handling mechanism. They are also designed for unexpected situations, as they try their best to allow an application to continually run after an error occurs. Last but not least, they can be identified using static code analysis, which means we require minimum aid from developers. As I mentioned before, the error code used by SWR must be recognized by a function's caller, which is illustrated in this figure. So as we can see, this shows the code from, again, Lite web server. And the function at the top, base64 decode, has one SWR, which is a simple return 0 statement instrumented into it. And when this function is got a called from its caller at the bottom, HTTP auth basic check, the SWR gets executed, so this function would immediately return to its caller, so that the caller can perform its own error handling correctly. So the return value used by the SWR must be recognized by the function's caller to ensure error handling can be handled properly. There are some approaches to identifying error code used by an application. Common libraries or API functions usually have documentations to state the error code. However, most code in the application does not have this kind of documentation. We might ask the developers to annotate each function for their error code, but that is tedious and time-consuming. So instead, we use heuristics to identify error code via static code analysis. So we first use two major heuristics, the error logging heuristic and null return heuristic, to generate or identify a list of functions that return error code. Then we propagate error code to more functions via information on the core chains. And eventually, we have an augmented list of functions that return error code, which are the functions that can be protected by SWRs. We have implemented our prototype, Talos, to mechanically generate and instrument SWRs into an application. And we evaluate security, coverage, and overhead of SWRs using 5 popular Linux applications, including web servers, web cache proxy, FTP server, and the database management system. For security, we want to know, do SWRs successfully neutralize vulnerabilities? And are they unobtrusive, which means they should not cause loss of major functionality. So we analyze the effectiveness and unobtrusiveness of SWR for 11 real-world vulnerabilities. And all of the vulnerabilities are successfully neutralized by our SWRs, and 8 of the SWRs are unobtrusive. And we have the details of the analysis of each vulnerability and its corresponding SWR in our paper. For coverage, we'd like to know what's the percentage of vulnerabilities that can be neutralized with an unobtrusive SWR. We estimate the coverage on vulnerabilities with the coverage on the code. And we tested 320 SWRs for their unobtrusiveness. So as we can see from the figure at the bottom, SWR can cover 76% of an application's code on average. And among them, unobtrusive SWRs can cover 53% of an application's code, which is over 2 times of the coverage of configuration workaround. Because in-place SWRs can increase code size and cause an application to incur runtime overhead. We also measured that. And on average, Talos adds 2% of code and causes an application to incur 1.3% of runtime overhead. So to conclude, SWRs can neutralize 53% of potential vulnerabilities and obtrusively, which is over 2 times of the coverage of configuration workarounds. And SWRs can be used just like configuration workarounds to neutralize vulnerabilities on the fly with a small 1.3% of runtime overhead. Last but not least, Talos, our prototype, can mechanically generate and instrument SWRs into existing applications, requiring minimum effort from developers. Thank you.
Hi, Talos MIT. So other than the name, what's different between this work and error virtualization, published 2005 and 2009 here at Oakland?
So you mean what's the difference? I'm not quite familiar with the talk you mentioned.
Well, you reference them in the paper, but you reference them wrongly. I mean, they still use return, values to escape bugs. It seems like the techniques are almost identical.
So what's the basic?
So the idea
of that paper?
The idea of using return values that are handled by the existing error handling code in the application, and sort of identifying these values, and recovering from bugs, has been done twice, once in 2005 and once in 2009. And you reference the papers in your paper, where you reference them incorrectly. So can you elaborate on what the differences are?
Oh, I see. Okay. So previously, the work that tried to identify error code in an application, basically they just try to say, either rely on the documentations of the application to know, what's the commonly used error code, and sometimes they try to use a certain default error code, say, -1, and in many cases, they could be used by, certain functions of an application. But we just found, this kind of techniques might not be, quite reliable because, different application developers, they might, choose the different error code. And we also found, even in the same application, different functions, they could, say, use a different error code to represent the same kind of error. So that's why we choose to use heuristics in our work to identify error code.
But I think that's also incorrect. There's been work that identifies using static analysis exactly how the error values are propagated, studied both in applications and the Linux file systems. And it's not a heuristic-based static analysis, actually more advanced than what you have. And that's also misreferenced in your work.
Yeah, that's a good question. Probably, yeah, we can take that offline.
So what are the main reasons for why not all vulnerabilities can be covered by SWRs?
So one reason is that basically we rely on the error handling mechanism, present in the application, right? So sometimes, due to the way an application is written, it probably don't have that many error handling code. So in that case, even though we try to, say, if one function does not have its own error handling code, we try to looking for error handling mechanism from the core chains that lead to that function. So basically, we can try to cover the function using its callers. But even in that case, sometimes, just certain function is written in that way, they don't have many error handling code in them. So that's one of the major reasons for some application, the coverage is not very high.